this panel. Hello, everyone. Welcome to the panel on performance and correctness tools for extreme scale computing. My name is Ignacio Laguna from the Lawrence Livermore National Laboratory, and I will be the moderator for this panel. This panel is going to be recorded and will be available later. So if you are the developer of a scientific computing application, you want to know about the performance and the correctness of your code. And for that, you do what most programmers do, which is to use tools to help you analyze the performance of your code and give you insight about the performance and the correctness. However, as we move into an era of highly heterogeneous systems with different classes of accelerators and highly distributed applications, possibly using different classes of workloads, scientific computing workloads and machine learning workloads, the existing tools have to be adapted to this extreme scale environment. And it could be the case that new tools have to be developed to help programmers be more productive in this extreme scale computing environment. And so the goal of this panel is to discuss tools in these two areas, performance analysis and correctness, in the context of extreme scale computing. And so we have put together a set of diverse and great panelists for this panel. Let me advance my, there you go. So each of them is an expert in at least one of these two areas. Performance analysis or correctness, and actually some of them have produced tools for the two domains, performance and correctness. So let me quickly introduce the panel members. So they will give more background information about themselves in their own presentations, but let me give some highlights of them. So we have Barton Miller. So Barton is the Vilas Distinguished Achievement Professor and the Amar and Bellinger Professor in Computer Sciences at the University of Wisconsin-Madison. So Barton has done has done research for many years on several aspects of tools, including software testing, security, binary instrumentation, just to mention a few of them. Welcome, Barton. So we have Heidi Pogson. So Heidi is a principal HPC applications engineer at Amazon Web Services, and Heidi previously worked at Cray and HPE as a distinguished technologist, leading the development of performance tools for several years. Welcome, Heidi. We have David Abramson. David is the Director of Research Computing at the University of Queensland. David has been doing research in HPC since 1979, which, by the way, is the year I was born. So I give you an idea of how many years of research he has in HPC. And many of his works are integrated into commercial products. Welcome, David. We have Todd Gamblin. Todd is a senior principal member of technical staff at the Lawrence Livermore National Laboratory. And he's the creator of the SPAC tool, which you probably know and are using in your systems. And he has done also research for many years on software engineering, dependency management, performance analysis and measurement. Welcome, Todd. And we have Marta Garcia-Gasulla. So Marta is a researcher at the Computer Science Department at the Barcelona Supercomputing Center. And she has done also research for many years on performance analysis. And she actually leads the best practices for performance and programmability group at BSc. Welcome, Marta. And so we have Marta and Heidi joining us remotely. And with this, let me give you more information about the format of the panel. So after this introduction, each of the panel members will give a short presentation where they will give more background information of themselves. And they will answer a number of questions that we have given to them. I'll read these questions in a few minutes. And then after the presentations, we will move into a Q&A session where we will take questions from the audience and from the And also we'll do a few polls. And all the questions will be through Slido, and I'll show you how to join a Slido. If you're on the hub system, you should see the Slido chat to your right. But if you're here, you can join with your phone, and you can submit questions as well. I'll show you how to join in a minute. So we have asked the panel members to give a position or an answer on the following questions. So let me read the questions. So number one, can we build tools in the face of increasing architectural diversity and rapid change? And if so, how do we do it? Number two, is there any hardware or software support required for these tools to improve programming productivity? And should HPC vendors provide such support, if that's the case? And number three, how should new tools be designed to be integrated, I would say easily integrated, into applications and provide actionable results to improve performance and correctness in applications? And so before we move into presentations, here's the Slido number. So if you are in the room, you can in your phone, you can go to slido.com, and you can enter this number, 991-684. Or you can also scan this barcode right now from the screen. I believe the barcode is in the back of the room. We were told it was going to be in the back of the room, but I don't see it here. So the best approach is probably just go to slido.com and enter this number. And if you're in the hub system in your laptop, you should see the same thing. So before we move into presentations, just going to give, I see people type in the number. Just make sure you are there. OK, seems like most people are there. All right, so we can now move to presentations. So this is the order of presentation. So first we're going to have Barton, then Heidi, David, Todd, and Marta. So I'm going to stop sharing here. We'll start with Barton.
OK, let me share my screen and see if I can get us into presentation mode.
Mm-hmm.
How do we look? We good there?
Mm-hmm.
OK, great. Thank you. First of all, congratulations to David for winning the Kennedy Award. That's quite a great honor, and he's definitely a gentleman deserving of that honor. So proud to be on the stage with you. And maybe I should let you go first because you're. I'm not sure I'm necessarily going to answer most of the questions that Ignacio posed. I'm just going to whine a lot. So, and because that's what tool people do, we whine a lot about things. So first of all, just some quick background. Part of my PhD, I worked on a tool called DPM, Distributed Program Monitor. Did message-based and trace it. It was a trace-based tool for message passing systems. And we did some interesting things like not just giving you numeric answers, which is something I like to think about, give you something actionable. We could actually come up with state diagrams of who talks with whom and how often in the system. And we did this thing called paths of causality. When I got to Wisconsin, we started building a tool called IPS, and there's still a great deal of debate about what IPS stands for. And part of what we did there that was notable was trying to give you, again, higher level actionable information, in that case, critical path analysis, trying to figure out what parts of the program were contributing to your length of execution. Just because you spend 30 minutes in one piece of the code doesn't mean if you fix it, you'll get 30 minutes of performance. So we're actually trying to deal with that. We're also trying to unify performance information based on the program structure, so data wasn't just data, but actually had structure to it. We moved on to IPS2, still didn't know what IPS stand for, but it was a second version, and started doing fine-grained clock sampling and using performance counters, and started using GUIs to let people navigate through the program structure. Many of you are familiar with Paradigm. We started this back when Jeff Hollingsworth and Bruce Irvin were grad students, and we introduced the whole idea of dynamic instrumentation, which now has taken on a life of its own, and the notion of automatically searching for performance bottlenecks. Push a button and go find them, something which I wish more tools had it. We got out of the performance tool business because there were too many of us in it, and we went into the component business and we took our binary instrumentation framework and turned it into an end product of itself. It took on a life of its own. It's available now on lots of platforms, x86, ARM, Power. We're working on a GPU version of it. And so we've become component generators, and we're inside of lots of other people's tools. And recently, we jumped in, we threw our hat into the CPU-GPU ring, looking at the interactions, not trying to figure out how to make a fast kernel or why your kernel's running slow, but looking at the time that's spent on data copying and synchronization between the CPU and GPU, and found huge things. We found programs wasting 10, 20, up to 50, 60% of their time just on CPU-GPU interactions. So that's kind of a quick summary of that. We also have some other components like MRNet for scalability, and there's lots of tools like the great stack trace tool at Livermore. It actually works with John's tools and some Cray products and things like that. So this is a bit, pardon me, of an incestuous community. We all work together and share stuff. All right. So I'm going to start the winding fest here, and I'll do it quickly so I don't waste up too much time for those of you who like to do it. Okay, obviously scale, thousands of nodes, millions of cores, and the scale's gotten bigger in some sense with GPU. Processors, the architectures can't turn the clock rate up anymore. They've lost that easy one, so they invent really deep hierarchies, out-of-order execution, things that make understanding and predicting and measuring performance more difficult. Well, of course, GPUs, accelerators, TPUs, all that kind of stuff has come along. So if it was hard enough trying to figure out how to deal with performance on millions of cores, and we have run our tools on millions of cores, now we have these odd devices that are connected to CPUs in odd ways. And people say, what about something like a unified memory model? There's no real shared memory currently between CPUs and GPUs in most domains, and that makes life even more interesting. We have too many programming models out there, and so if you want to present performance data in terms of the idioms the programmer is using, you have to understand too many different idioms, and so that's a challenge. We have to often live on the same nodes the program's running on, and so we end up fighting the nodes for buffer space and processes running on the nodes to collect data and things like that. That makes life more interesting. Launching your tools in environments where you're not arbitrarily running on a node, but you have to live side by side with an application, a job launcher. That's fun. And often our only place for storage is the parallel file system, which often have funny semantics. And okay, we know, so that stuff's all, none of that should be surprising to anybody in the tool business. And I'm part of the DOE ECP project, and it really stresses me out. I said, 5 years ago when we started looking at being part of it, they said, would it be fun if they chose each different computer with a different CPU and GPU? Well, they didn't quite do that. But if we look at the 3 exascale machines and Perlmutter, which is a pre-exascale machine that's coming up now, we see AMD EPYC, we see Intel Xeon, and we see AMD Milan. Okay, that's kind of x86-ish. Can't whine too hard about that. On the GPU side, we see AMD Radeons, Intel Ponfecchios, and NVIDIA A100. So that's a challenge because the GPUs are hard and the tools are completely different on each one of those. And of course, Lanel's building their own machine, running their own way on that side, which is using the new NVIDIA Grace CPU-GPU model, which is really intriguing, but totally different than everything else. Okay, so we're already doing something really hard here, and now we have to do it differently on all these platforms. So, God help us. Let's not be too jingoistic here. Let's criticize the Europeans too. We have the Euro HPC program, and we have an AMD and an Intel Ice Lake machine. One's running AMD, one's running NVIDIA. I'll let Marta decide if she wants to tell us about what's going to be in Mare Nostrum. though you hear ARM and RISC-V thrown around a lot, so I'm not sure if there's anything I can say there. You'll have to decide if there's something public you can say on that end. Of course, in Japan, there's a great exaflop single precision machine, about a half petaflop, and that's using ARM with the SVE extension, so that's again different. China has its own roadmap with their own processors. Some of them are derived from our processors, some of them quite different. So if we're trying to develop tools and we're an international community, there's a lot of variations there. OpenCL, CUDA, HIP, kind of like CUDA, MPI and OpenMP, Charm, Legion, and just because we didn't have enough to do, we're throwing in AI and ML into all these machines, and we're creating whole new performance models and trying to profile machine learning like a deep neural network and presenting reasonable information to the programmer to improve their performance is a totally different thing. And I don't think we even know how to do that, nor does the ML community know how to do that. So, and I was just at a workshop 2 weeks ago at Dagstuhl. We're talking about adaptive computing. So systems are going to adapt on the fly, dealing to changing compute and power needs. So your partitions will change, the allocations will change while your application's running. So if we couldn't do it at all statically, now we won't be able to do it dynamically either. No, I didn't say that right. If we could do it statically, we will be able to do it dynamically, hopefully. So we just keep raising the bar on the things we're doing. I told you this was going to be a whining fest, and that's kind of where I think that's the average tool builder right there in that picture. And with that, I will free up the screen and let somebody say something less whining like.
Thank you. Very interesting. Thank you very much, Martin. All right, so following, we will have Heidi's video. I'd like to ask our AV people to present Heidi's video.
Hi, my name is Heidi Poxon, and it's a pleasure to be here on the panel today to talk about performance and correctness tools and how we can advance them for our next generation supercomputers. So first I wanted to just tell you a little bit about myself. I've been in the HPC industry for most of my career. Early on in my career, I realized that I like to make things go fast, and so I ended up working as a developer on different parallel processing software, programming models like the Cray auto-tasking software that eventually transitioned to OpenMP. And I was an MPI developer for many years, working with several different high-performance networks. And then until recently, I was responsible for the Cray performance tools, or CrayPat and Apprentice2 and Reveal. And one of the things that I found most valuable is the chance to talk to customers and sit down with customers who are using the tools to understand what was intuitive, what was not intuitive, and how they could learn to extract performance from their application and from the systems as they ran. And so with that, I just wanted to first remind myself and others that no matter how well you know an application, your application, once you move it to a new platform, especially on these next generation systems that are just getting more and more complex with the architectures, there are a lot of factors that can impact the performance of an application. And so because of that, it's very important to have access to tools. So I'm going to mainly talk here about performance tools. I know others on the panel will talk about correctness tools. And so I wanted to just mention at first, it is very valuable to have a performance tool that you can profile applications with. It really doesn't reduce your time investment when you're performing optimizations. So rather than spending a whole bunch of time in a certain area of the code, revising an algorithm to hopefully make it run faster, only to find out when you run your application, there's no performance change. A tool can give you the guidance to find your top bottlenecks so that your efforts are better rewarded, so that you do see overall performance improvements when you remove those bottlenecks. Also, you want a tool that meets the application where it is. And so if you have an application and you want to run with, say, 500,000 MPI ranks, or maybe that application runs with 100 MPI ranks, it's important that the tool can profile where that application is going to run or with the number of resources so that you can find the bottlenecks that are most critical to performance. Having simple interfaces is also important so that you can quickly obtain a profile of where or what the most important areas and time-consuming areas of code are. But you also want that tool to be able to dive deeper and understand the whys into a performance problem. And finally, one of the things that's important with tools is the ability to scale out knowledge of an architecture. So if an application runs with a particular tool, that tool knows hopefully about the architecture, and it can look at the data collected and provide some actionable guidance that allows the user to not necessarily have to know everything about that architecture. That could be the tools burden, so that it could be a little bit easier to handle the different systems you're running on. So today I would like to introduce a few challenges and talk about a few challenges here as we go through the panel. The first thing is my realization that the performance tools are really periodic use tools. That's not using a performance tool or a profiler is not like using a debugger or a compiler, which you use more often potentially. The optimization phase is not as commonly run with applications as other things like editors and especially compilers. And so recognizing that ease of use of a tool when it is time to profile is critical. And having tools that don't have a large learning curve to be able to learn about the bottlenecks is very key. As we go to more diverse architectures and we have things like accelerators and CPUs and complex memory hierarchies that we're trying to scale to even higher numbers, and as we move towards exascale, we realize that there's no one performance tool that fits all needs either. Just like there's no one compiler that works for every HPC application, it's good to have a variety of tools and choose the best one that works for you. And so one of the things that's been successful as we've moved from gigaflops to teraflops to petaflops and now to exaflops is to have building blocks for tool developers where there's some common components that we can take advantage of as we're developing tools. Things like PAPI or MRNet or even GDB for building on top of other tools. Having the ability to have these building blocks is something that's been very useful, and I'd like to see that continue. Another thing is performance counters. Performance counters have been something that are very difficult to manage and corral and understand as you get to different processors and different accelerators. And one of the things that would be nice to see is if there was a better connection and better information from vendors that described the counters, not maybe all of the counters, but a select set that are key for profiling. Things like, how does this counter really behave? Does it include speculative instructions or not? That sort of information is something that tool developers tend to have to go find and figure out, and it would be nice if we had some better solutions in that area. And finally, the last thing I wanted to mention is the connection of profiling with an application. So one of the most challenging things that I've found is I have, when I've gone to a customer, sat down and we have an application that's running correctly, getting correct results, and we're ready to profile that code, all of a sudden we say, okay, rebuild, we're going to profile now. And it turns out it takes 8 to 12 hours to rebuild the code. And so you're done for the day, and now you have to wait before you can actually get any results. And so I'd really like to see a collaboration between tools and applications so that the applications were more ready to profile at any time. So for example, always having symbols included, even though you're fully optimized, and considering frame pointers and not the omission of frame pointers, so that it just makes things easier to collect information from the application. So this is another area where I think that we can improve, is being able to easily connect in a profiler to an application. One of the things that's been happening is dynamic linking is becoming more popular now in HPC. It's taken a while on supercomputers, but that's been very beneficial as an example to linking in a profiler into an application without having to rebuild. And so with that, I wanted to just introduce these few things, and then I'd like to pass it back to Ignacio for the rest of our panel discussion. Thank you for your time.
Thank you very much, Heidi. Very interesting. I like the challenges that you mentioned. We'll get into details later on the Q&A. Sorry, there was a problem in the beginning of your talk. We were not sharing the screen in the beginning of the video. It was shared in the room, but it was not shared through Zoom. But I guess we fixed it in the middle of it, and most people were able to get your main points. All right. So with this, we are going to move to David's presentation. So,
okay. Yeah. Oh, we had 2 Davids this morning, right? So, hang on. Let me share that guy. I think. Yeah. Does that work?
we got you. You can share. Mm-hmm.
Yep. Okay.
Hello.
Oh,
My name's David
we're doing that
Abrams
one, are we?
from the Research Computing
Oh, no,
Center.
sorry. I'm sorry.
That's
we are
fine. Let it go. Let it
I'm
go.
going to talk briefly about our work in extreme scale performance and correct.
Let it go.
You just can't
Share
do
it.
it here. You probably should do it live. So.
Do we? I was
Sorry, I asked the audio people to play your video, and then you asked me to present. We can do
We can do
whatever.
both at the same time if you want.
Let's do it live.
Which one do you
But I'm
want?
here, so let's do it live, right?
Okay, so Dave is gonna present here. I'm sorry.
Yes.
We don't have to play the video.
Let's try again.
You can do the two and compare the difference.
Yeah,
with
yeah,
your
very
device.
good, Bart. There it is. Why can't I get... Sorry, I've lost that screen. Oh. Just give me a sec. I can't find the...
We can see your screen.
We
That's
can see
fine.
Yeah, but I can't control it.
Oh, you can
Because I
control
can't
your
find it.
slides.
It's got to be there somewhere. Ah, here it is. Okay, it's hiding under there.
Mm-hmm.
Yep. Never do anything live. Okay. Let's do this. Sorry. Okay, is that one? Share that. Right.
Yep.
All right? Okay.
Yep.
Whew, I'm exhausted now. All right, so I didn't answer the question, so I'm with you, right? But I'm not going to whine quite as much. So I want to talk about some work we've been doing over the last many years and how that plays into this whole area, I think. I think there are 2 main challenges that jump right out when you're debugging at scale. So one is what we're calling a cognitive challenge, and the other one is a performance challenge. So I'm talking about debugging rather than performance profiling. So the cognitive challenge comes about from the fact that there's just so much information at scale that you can no longer process it as a poor mortal. So, and I'll show you some examples a bit later where previously we might, the best case debugging is, well, print this thing out. And print clearly doesn't scale to the scale of problems and the scale of machines. So what debuggers have tried to do around, over the years is add functionality that allows you to see processes, but then in these big machines we just have an enormous number of threads or processors actually running at the time. So that creates one challenge, and the traditional technique for a UI-based debugger is to try and overlay that on some sort of UI, but then we start to run out of pixels ultimately on the number of cores that we're actually looking at. So that challenges the UI. At the data end of things, the data structures that we're manipulating in these codes are also enormous. So whilst the control threads are complicated and you're trying to visualize that, the data structures themselves are also large and very complex and often numerical floating point type structures. So it's infeasible to print out what the techniques that work in the small at scale. It just doesn't work to say print out this structure or look at what's in there. And even if you did, you just finish up with enormous numbers of floating point numbers. So that doesn't scale out well. The other problem we have is a cognitive one, is in the heterogeneity that Bart talked about in the underlying platforms. So that causes a few challenges. First of all, the heterogeneity is often the source of the problem. It's when we put something onto another machine and it no longer behaves the way it used to behave. So that heterogeneity in the underlying platform introduces errors. And then also the heterogeneity creates huge challenges for the tool builders, because we've got to straddle such a wide base. So they're the ones we classify into cognitive challenges. And then the other one is that as you start to think about more complicated debugging techniques, and I'll show you some, they start to become a performance bottleneck of their own. So high-level debugging becomes expensive, and ironically, the debuggers that we've run to date traditionally drop back to one node, and so they don't necessarily utilize the underlying platform. So imagine having 1 million cores running something, and then the debugger stops back onto the front end and says, okay, so now what do you want to do? So you've got 1 million cores theoretically stopped, not doing anything useful and not helping the debugger. So in the extreme, all of those things become worse. So some years back, we started playing around this idea of data-centric debugging, where you're trying to debug the data structures and the data flow within an algorithm rather than worrying too much about what the actual control threads are doing. So I mentioned before that what doesn't scale is printing out values, and you can see in the left side there that we're printing out a few values, so that's all very nice, but when things get very large, that doesn't work out too well. So we've done quite a lot of work over the years using scientific visualization techniques to try and show what's happening inside complex data structures. And I'll show you on the next slide a little bit more about that. So, two-dimensional data structures, you might do pixel maps, and then three-dimensional structures, you might draw volumes, and then higher dimension becomes problematic, but at least we've got some sort of handle on it. We're not necessarily looking at each individual data value. This is a slide I actually showed this morning for anyone who came to my talk, and it's quite an old slide. It's one that we produced when we were debugging the port of a parallel climate model from one machine to another, and errors were introduced. And I think more often than not, when you get small errors in a large numeric code, people say, oh, they're just floating point differences. Well, it turned out that this one wasn't just floating point differences. So what we've done with this data-centric approach is take the difference between data structures at runtime on two programs, actually potentially on two different machines, and compare those. And so this data-centric debugging idea says that you can narrow the region in which things are failing by looking at where they're actually differing between two executing codes at runtime. And then if you go one step further and you visualize that, you get a lot of power. So in the top right corner, I'm showing the difference, an isosurface of difference between the temperature variable in two three-dimensional climate models. Okay, so we're not showing the absolute values of temperature, we're showing the difference between the two models. And then we draw an isosurface around it and say, show me everywhere the error is greater than a certain amount. Now, I took that picture and I showed it to a colleague who's a climate scientist, and he said, I don't think you've got one error, you've got two. And he said, because the physics that's going on at the top of the atmosphere, that blob at the top, is different from the physics that's going on down the bottom, and they're different pieces of code. There's another visualization we show down the bottom here, which is a time-varying version of that, and you can see the error actually evolving in time. And so it starts out down the bottom, and then suddenly this hot dog, we called it, was growing at the top. Now, there's no way in a time-stepping differential equation code like that, finite difference code, that you can get from the bottom of the atmosphere to the top in one time step. So his conjecture was that you have two different errors evolving in time, and they're not actually related. I took that back to the group doing the port, and who looked at the code and said, actually, yeah, that's actually correct. So it turned out some of the physics had changed in the planetary boundary layer, and some of the radiation code, which is at the top of the atmosphere, was different as well. So that kind of was like my, that was a great moment. eureka moment, because it showed us that we could show a picture to someone who hadn't even seen the source code, and they were able to reason about what was going wrong inside that code. Here's another version, another example where we've got two codes that are modeling. It's a two-dimensional particle code where you drop a brick into a tank, and the top one is one code, the bottom one is another code. The blue is not greatly visible, but if you just look at those, you'd say, oh, they look the same. But actually, if you take the difference and you visualize the difference between where every particle is, then you start to see differences emerging. And as that video runs, you can actually see the red region growing as the times, so that you start out with a small error and then it actually propagates through the region. And if you look at it for long enough, you can actually see boundary errors happening where process alignment, where data structures are decomposed. So you get a lot of power from that. The most recent work we've done is to say, sometimes then the structures get so large you can't even visualize them like that. So I had a grad student looking at computing statistics, and more recently he's got interested in machine learning algorithms that look at the data and try and reason about what's going on inside there. So this was an example of a particle code in which we compute a histogram of, this is a Newtonian mechanics code, so looking at the speeds of particles that are moving around and then making assertions about what that distribution should actually look like. And this error was spotted by the fact that there were actually too many high-speed particles in there. So when you can start to write assertions about the data structure and allow the debugger to reason about what's going on inside the code, that also becomes very powerful. Now the problem with all of that is, and I started out by saying that as the debugger gets smarter, it actually gets harder to build. So we spent quite a lot of time working on how you scale this out, and this is I'm not going to step through this, but this is a schematic, in fact, of what our debugger looks like. And Bart will be happy to see there's an MRNet tree in there, so we're building on top of other tool builders. But basically what we do is we run a debug server right down on each of the nodes, and it's accessing the state of that part of the computation. Some of that code can be on a GPU, and so we're using a version of the debugger that actually accesses the state inside the GPU. And then that information is pulled up back through a reduction tree to the debugger, which is running centrally, so that you're actually starting to get parallelism within the debugger itself. So if the debugger is saying things like, this data structure should equal that data structure, then you can decompose that and do the comparison in parallel across the machine, and then just filter back the results up through a reduction tree, rather than trying to take the whole state, which has been decomposed onto hundreds of thousands of cores. There's no way you can actually put all of that state. So you start to do a lot of things around how you build it, how you scale out the debugger itself, but in the limit we find that the debugger itself is running on the parallel machine. So whilst it's stopped, not running the code, you're able to use those cores to in fact do compute. Here's another view of that same thing. We did some work on how you compare data structures between running codes when you don't actually want to ship all of the data back. I won't go into details on any of that. And so there's a version of this, Heidi was in her previous life was working for Cray, so we worked with Heidi on implementing a version of this on Cray, so it's called CCDB. And it's got a lot of stuff in there from all over the place, so using GDB and various versions of that for actually accessing the state of the underlying code, CUDA GDB for talking to the GPU cores, MRNet for doing the reduction operations. We built a scalable library on top of that for doing distribution of debugger commands and then reducing the results back. And one of the other things we've spent some time doing is normalizing the data across different platforms, because it's all very well to compare data between two platforms, but they're not necessarily the same. So I'll stop there and we'll move on to the others. Okay.
All right. Thank you, David. Very interesting. I like this idea of differential debugging and stuff. We'll talk about in the Q&A. All right, so moving on, we have Todd's presentation.
Okay.
Is his presentation ready?
Yeah, it's all ready. Okay, so
I'm going to take a slightly different tack on this. I'm coming at this from the build angle, and in fact, people know me as the person who made SPAC, but I actually made that because I had a grad student who kept trying to build things and they kept breaking. What she was trying to build were performance tools, and so, I have some. I know how hard these things can be to use, and so if you look at modern applications, they're not at all simple, right? Like there's little finite element libraries are 31 different packages now that have to be linked together, and neural net frameworks are more dependencies than that. 71, TensorFlow is bigger than LBAN. And then our multi-physics codes are really lots of different codes linked together, and these things can be over 100 different packages that you have to build and get working with tools. And so if you look at what the libraries have had to do to work on GPU platforms now, so MFEM, that finite element library that I just showed, it has more configurations than the one that we showed now that we've had to support 3 different exascale architectures with it. There are now a whole bunch of libraries in the middle. It used to be just linear algebra, mesh, and finite element. Now it's got a split memory model with the kernel execution is split. The memory structures are divided into read, write, and write, and then all of those are mapped to like 6 different backends that run on GPUs and CPUs. And so you can run this thing in lots of different configurations, but there's all these different runtime libraries that you have to care about in the middle, and there are lots of configurations that you care about for performance. You have to run this thing with the one that performs best on a particular machine, but you don't know, so you want to be able to experiment with those things. And so that's what we try to do. But the experience for using performance tools typically looks kind of like this. You have a performance problem, you try to build with the latest tool, it explodes, and then you have 2 problems. And so I think the way to solve this is not to continue hacking build solutions in left and right. It's actually to be able to reason about that stuff and to come up with a model for builds so that we can actually understand what's being done. And so if you look at package managers, they actually have models for this stuff. Most of them are pretty simple. They have like a version and a name of a software package for each node in the graph. But they lack things like compiler runtime models, CUDA, ROCm, all the other things that we deal with. All of these things for most stacks, for most tools for building software stacks, or for building even applications, the build system makes you pick them up front. It's basically, the tool chain is an assumption. All the things built into it are things that are sort of black magic that application developers shouldn't have to deal with. And oftentimes compiler developers do awful black magic things underneath the compiler. There's nasty things that happen with like C++ runtime interfaces and even, let's see, so compiler interop is a huge problem because making sure that all of the machinations that one compiler did behind the scenes are compatible with all the others is extremely difficult. So yeah, we need more general models for these components. And if you think about what a package manager does, it's the core thing that it does is try to make sure that a graph of dependencies is consistent. And that's exactly what you need to get tools building correctly with our codes. If you know, for example, that a code is built with a particular standard C++ runtime library, and you're trying to link in a C++ tool with it, well, you're going to need to know that the runtime libraries are compatible. And so you should be able to actually model that in the graph. Or if you know that a code was built with a particular version of the Intel compiler and it used the runtime library from a particular GCC version, that's the kind of thing you need to know to build a tool. It's way lower level than what the application developers are typically doing, and it spans tool chains and runtime libraries. Is there any necessary hardware and software support required for this stuff? I think we need general interfaces for things like instrumentation, so compiler wrappers and stuff like that. Right now, a lot of that is really up to the user. So if you think about like sanitizer tools, which are the big ones that we face now in the correctness land, you have to build, if you have a code like this with like and go back to my first slide, if you have a code with 115 packages and you want to use a sanitizer with it, you need to build all 115 packages with the sanitizer. And most people just say, no, I'm not going to do that. I can do without the sanitizer. I don't care about it that much, and they hack at it. And so if you want to be able to instrument a code like this, the thing needs to build in some framework, and you need a common interface for inserting that instrumentation in the code. And so, just in SPAC, we have compiler wrappers that it uses to insert some fairly trivial things, So it sets search paths and it sets R paths for the things that it's building, so that when you try to run it, it runs with all the libraries that you built it with. I think tools could benefit from that kind of thing too. You could basically have a standard interface where our wrappers are used to inject further tools into the build, and basically we provide a standard interface for that. So, I think, I've sort of covered the last question already, but yeah, I think the way that tools ought to be designed is that there need to be frameworks for the actual build process for tools. They're packages like any other, but the dependency relationships for these packages aren't as well understood because we're really at a lower level. And so you need to move towards tools towards package management tools that can handle this. So like right now we handle build, link, run, and test dependencies in SPAC, but we don't handle compilers very well because they're essentially build dependencies that change the way the code is generated and put a link dependency on some runtime library on the code. So we're trying to model that better. Sanitizers and things that tools that change the code or insert instrumentation, that needs to be some sort of metadata that's inserted into the model so that you can actually check that the instrumentation you're doing is compatible. So that's something that we're working on modeling in SPAC. We're trying to add this first-class support for compilers, and then another thing that I think is going to come up even more on El Capitan, our exascale system that we're going to have at Livermore in 23, is there are consistency rules across the build that we have to take into account. And so there are compilers that generate code in a certain way that says that all other code that's linked with it has to be built in a certain way. And there are things like the linker, which no stack that I know of models very well. Certain types of optimizations that modern compilers do, especially now that we're using accelerators, require a bunch of link time stuff, and tools often try to wrap the linker, and I think all of that is going to break when we start using accelerators. I think that's going to, basically you're going to need to be able to express the requirements for your linker much better so you can evaluate consistency across a graph. And I'm not getting into it here, but the way that this, that we're trying to model this is we're looking at tools like ASP or SMT or solvers that sort of expand on what a basic package solver would do, but allow you to insert more semantics into it. And so I think I'll leave it at that. But it's a really hard problem. It's NP hard, and we need to be able to reason about this stuff.
All right. Thank you very much, Todd. I definitely relate to that example of a graduate student trying to build a tool. I was one of those at some point trying to build, I don't remember what tool, was probably a source-to-source translation tool, and I couldn't build it and I couldn't use it in my research. So yeah, like that example. All right, and then finally we have Marta's presentation, and for Marta we're gonna play the video that she shared.
Hi, this is Marta Garcia from the Barcelona Supercomputing Center. I have been doing research in HPC since 2006, and my research interests started being in load balance. Also, I worked with programming models, and lately I also got very interested in performance analysis. Currently, I lead a group in the computer science department of the Barcelona Supercomputing Center called Best Practices for Performance and Programmability. The aim of this group is to be a bridge between the computer scientists and the field scientists that do research using HPC. Between these two groups, there's a wide gap that we try to make smaller. The main problem is language, of course. As you know, sometimes it seems that we speak different languages, but it's not only language and understanding each other, it's also about the problems that we try to solve every day. So my idea is to try to solve the same problem so that computer scientists really try to help application developers. To do this, I rely on performance analysis, doing performance analysis of real HPC use cases. I obtain very valuable information for application developers on how their applications can be modified or can be executed to obtain better performance and be more efficient. But at the same time, with all those performance analysis that we do, we get also information and insight for computer scientists, for designers of programming models, for computer architects on how to build these machines and how to program them and which are the real problems that HPC applications are facing and what they can do to help these applications. So to this panel, I bring the point of view of a performance analyst as a user of performance tools. And also I try to bring a bit the point of view of these application users and developers. So yeah, it's true. HPC systems are growing, and they are growing in two ways. They are growing in the diversity and variety of hardware and also in size. So talking about the diversity of hardware that we are getting these days, I think that we need to isolate all this diversity and all this variety and all this new hardware that appears from the application developers. So we have applications with thousands of lines of code that we cannot expect them to change it every time a new architecture appears. So I think that the effort needs to be put in the system software, in all the layers of the system software, to isolate the applications from these changes. And performance tools are one of these software. Performance tools need to be agnostic of the architecture and portable, so that the application and the analysts do not need to worry about the architecture where they are working. And this, of course, means all the software that we rely. So it's hardware counters. We need to get a minimum set of hardware counters that we can obtain everywhere, so that we can measure the same kind of things in different architectures. So talking about a size, the size of the machines that everybody is so worried now because of we are getting to exascale. So I say let's keep it real. So let's analyze, let's focus on real runs. What do real applications need? Which are the real runs that they do? Which is the size of those runs, and what do we need to analyze them? And I think for application developers or for users, the most important thing is not the size of the run that they are doing, but it's more on the insight that they get when you analyze their application. So it's, if you analyze like a very big run, but you cannot give them any valuable information, on the other hand, maybe you can analyze a smaller run, but give them insight on how to make that application perform better. So the important thing is the insight that you can get from those tools. And this brings to me to the idea that you need to run, of course, you need to analyze very big runs, but and to do that, the only way will be to reduce the amount of data that you collect. So you'll need to aggregate things. You won't be able to get all those details. But at the same time, to getting inside, sometimes we need a very detail of what's going on in the application. So when we do the performance analysis, we sometimes need to look a lot into the detail on what's going on to understand the performance. But at the same time, we need the global picture of what's going on that simulation or that execution. So I think that's one of the big challenges for the tools, that they need to be between these 2 points, very extreme points, where you are able to get data for very big runs that gives you a lot of data that maybe it's not necessary because you can just work with some aggregates, and at the same time you need a lot of detail. So how to travel between these 2 points, the big runs with a lot of data and the very detailed to understand what's going on. And to finish also, regarding the tools, I think that we need also to focus a lot on the methodology and the kind of methods that we follow to do this performance analysis. At the end, tools are just tools in our belt that allow us to do an analysis. But if we don't know what we are looking for, if we just get numbers aggregated, that doesn't give us any insight. So we need to to learn how to analyze and to provide methodologies and to teach to make these tools useful.
All right. Thank you very much, Marta. I like this idea of data aggregation a lot. I think we need more of that. Moving forward. Okay. So with this, let's start taking questions. So we have a few questions here in Slido. Okay, they are sorted by I think. Okay, let's start with this one. So OpenMP has defined profile and debugger interfaces that implementations must provide. And as such, are such interfaces useful? And is there's any evidence to support that?
Well, I'll start with that one. Anything that makes life easier, and thank you, I assume that's Michael Wolf from NVIDIA there, heckling us. No, contributing, I'm sorry. That was, anything that makes performance data easier to gather is a good thing. And anything that gets rid of the diversity in the interfaces to collect performance data makes our life easier. And that's a good thing. And so the good news is that if you want OpenMP data, and if the data you want about OpenMP programs is available from that interface, this is going to make your life easier. So there's a base set of information that you should be able to gather more easily. The problem is that's OpenMP, and if every programming model out there gave us that same kind of open interface, then life would get easier for us. And if those interfaces were somehow similar to each other, that would make our life even easier to get. But that limits the things that you can gather easily to the things that the OpenMP designers anticipated. If you want to gather things at a different granularity in a different way about different events, then you might not be able to do it. I mean, I like to pick on NVIDIA. They're very successful. Their stock prices are going to go down if I pick on them, so that's okay. That NVIDIA provides some very nice interfaces, CPUGPU, for example, but CPUGPU by far doesn't tell you everything, and sometimes it lies to you horribly, and sometimes it just doesn't tell you certain things. And so having it is way better than not having it. But it's not the end of the story. If you really want to do some other kinds of performance analysis, you may have to go beyond that.
Also, CPUGPU, like, at least at one point or another, turning it on resulted in a whole lot of overhead in the form of threads in the background. And I think, like, understanding those aspects of the tools, especially when it's behind an opaque interface, is important for performance too. So, I mean, yeah, it's helpful to have the interface, but like David said, if it perturbs everything, then that's now you have two problems.
Mm-hmm. Right.
So if I could jump in really quick too, just for a minute here, I wanted to say OpenMP was a good example that was brought up. I like to see an interface with the different programming models because it's the way to help the tool get back to the user source code. It does no good to say, here's a bottleneck, it's over there somewhere in your whole application, right? And so it is a key to tell us how to get back, how the breadcrumbs to get back to the source of the bottleneck and where that lives in the code. The other thing too, having these interfaces is really important for OpenMP. Specifically, one of my frustrations was explicit versus implicit barriers. If you want to calculate overhead that OpenMP incurred, it wasn't always easy to find the implicit barrier overhead. And so having those little breadcrumbs like that from a programming language or model, whether it's OpenMP, Cocos, Raja, whatever, I think it's very beneficial, as Bart said, for tools.
Yeah, having it in terms of the programmer's model is crucial, and mapping it up. And one of the big challenges of doing that is a lot of the way we program is in a data parallel sort of way. And actually one of my students a long time ago, Bruce Irvin, was looking at the idea of how do you present performance information in terms of the data structures, not in terms of the code. You know, where does time go? Which arrays, which structures? How are we getting implicit movement of boundaries of arrays or sections of arrays moving around? And we're still somewhat weak in the area of getting performance interfaces and performance tools that are giving us data views of performance, not just control views of performance.
I agree.
All right, yeah. So I'd like to give a point here. I mean, I'm the moderator only. I'm not supposed to give
Oh, no,
opinions.
we want to hear your
Say something.
But
Go for it.
I participated in the standardization of the OpenMP tools interface, OMPT and OMPD. And I can give you evidence of tools that have used this interface, Michael. I know HPC Toolkit uses the OMPT interface. We have in Livermore also developed a few tools for data rate checking. One is the Archer tool that does data rate checking that uses the OMPT as well. So there are tools using these interfaces. So that's evidence that standardizing these interfaces for developing tools, I think it's something useful. All right. Okay, we have several other questions. So let's see. We have one for Haiti. No one tool fits all. Is this because of different types of information being collected and processed, or because of architectural differences?
Something else?
So I think there's two things that come to my mind. The first is that there are different types of information collected. So one of the examples that I can think of is when I was at Cray and working on CrayPat. That tool was designed to do a whole program analysis, find the major bottlenecks in your application, and then when you wanted to dive to a real low level, for example, to analyze how your code was behaving on a particular kernel for a GPU, for an NVIDIA GPU, we would oftentimes recommend to go to the low level analysis, go use an NVIDIA tool. Because a processor vendor or a GPU vendor has the ability to maybe know more about their architecture and provide that information through to the tool. And so from that, I mean, no one tool fits all, but then the second area is different tool developers tend to focus on different things. Some tools are designed to really focus on a particular processor architecture. Some tools are designed to work across all architectures that are available to supercomputing. And so it really depends on what your goals are for where your application is going to run and how you want to use it.
Yeah. And as we move into more programming models and extreme scale computing more and more, I guess the question I will have is, should we continue with this idea of having different tools for different problems, or should we work as a community in more standard ways to, I don't know, standardize interfaces like the OpenMP example? That's one case.
Well, I think there's two things there. I mean, the thing that I mentioned sort of at the end of my opening statement is we're dealing with this machine learning environment, and machine learning people are struggling and working on the whole idea of model introspection. Your model does something and you get 90% accuracy, or you don't get 90% accuracy and you wonder why, or the model's running slowly or running fast and you don't know why. And so they're trying to actually figure out what that means. This is, from the performance side of it, I don't know anybody that's looking at how do you make your models go faster, and I don't see any work on the DNN library world, for example. I'll pick on DNNs because they're the most common ones we like, to say what's a uniform, not only what's a uniform interface for providing the information, but what the heck information can I provide to the user that'll be meaningful to them in terms of their learning model that they can then use to transform that learning model to be more efficient. So I think we're all struggling with threads and message passing and parallel loop constructs and things like that, which we all understand pretty well, and we're pushing a lot of that's down into the GPU, vectorization, is something we understand at various levels. But now we're we're being pushed into domains that are just completely alien to us.
Please. So you said that nobody's working on making models go faster?
Pardon?
I mean, there's...
I'm not saying people are tuning models all the time.
Yeah.
I'm saying coming up with reasonable interfaces for extracting information from models to understand their performance and ways of mapping that to the user to do that. I think that if there's somebody out there, I'm looking in the audience, I don't see people who are likely to be PhD students maybe, but I think if you're looking for a great PhD topic is take the kinds of goals that we've had in the HPC world and let's push them in the tools world and push them into the machine learning world. There's a lot of traction to be gained. Plus, you'll have at least 5 offers of a startup if you're successful.
Actually, I mean, I was talking to someone from Facebook yesterday, and they have models that basically the performance is data dependent, and they're trying to get the code to be tuned basically dynamically to pick the right version of an evaluation routine or a training kernel or whatever for the data. And it's very, very similar to some of the stuff that we've considered for like multi-physics apps. So yeah, I think that could be super beneficial.
There were a couple of other aspects I thought I'd throw in at this point. So one of them is I think we still have tools that are too low level and not well matched to either the problem domain or the, get closer, better, the problem domain or the programming language. So, take for example, we've got counters that give us cache hit rates. Well, if I'm debugging a large code, it's really, really hard to see. It's the point you were making before about, you want to know which data structures are actually thrashing, not the fact that the cache hit rate at this point's gone high. So that was one thing, aspect. And the other thing I was going to pick up on there's a slightly different answer to that same question is, I can't talk. The other thing is, we produce lots of tools and they're all different. And I don't think, Eclipse the guys tried to produce a framework where you could drop tools in. And we've kind of gone away from that. So what happens is, I need the tool of choice for a particular problem, and now I've got to go and learn a whole new tool and the like. So I think standardization around that would actually help quite a lot if you ran the tool the same way and all of the things that are common were in the same place.
Right, yeah. All right, let's move to the next question. Do you think tools in general should be geared towards scientific application developers more than performance engineers? Who would like to take that?
I think tools should be targeted towards anybody that's willing to take the time to use them. It's actually a funny question because if you're a performance engineer, you're being paid to do performance, and you'll use anything at your disposal, including your deep knowledge of the architectures and a great deal of black magic to make the code run faster. If you're an application programmer, the question is, will you perceive using a tool as a pathway to get more science done? And if you don't perceive it as a way of getting more science done, you're not going to use it, and you may not even be aware of what a tool can do, or maybe you tried one and you tried to install and the install failed, and because they usually do the first time, and you say, I don't have time for doing that.
I give up.
Yeah, and so they're really different communities, and we don't need to worry about performance engineers because they're kind of a captured audience. But we do have to worry about scientific programmers because they're scared. I mean, if you're in a facility like Livermore, I'll take, you have a great performance staff as part of the lab, and sometimes you have the success that people walk between buildings or hallways and talk to you, or sometimes you impose yourself on them, or they ask you in, or some manager kind of makes a marriage there, and that's the best. But if you're out there in a small organization without a performance staff, then there's a whole bunch of challenges that are not technical at all.
I think we've had a lot of success, like Matt's here in the audience, so like with Matt's tools, because we've focused on higher level stuff for application developers, and we've basically worked with the teams to sort of get them to link our tools into their code, so that we have continuous performance monitoring. And basically, like every week, they say, "Here's the profile. What are the hotspots? Let's focus on those this week." And then the experts take a deeper dive into that part of the code, but at least the team understands which modules are slow and how oftentimes they have to help us with improving them. But I think you need that kind of relationship, otherwise, it's not, I think there's going to be performance problems that application developers can't fix.
What do we do for organizations that aren't as well provisioned as a place like Livermore?
I guess I would say, like, at least with like Caliper and Hatchet, like we've made it pretty easy to link that stuff in your code and get a really high level, view of the profile of one run. And there's other ways to do that. So I would say you can get pretty far that way. Right?
I really like groups like Al Maloney's team, Samir Shende at Tau, or John Melacrummy's team with HPC Toolkit. These people travel all over the place, and they go to workshops, and they go to universities, and they go to people's facilities, and say, let's sit down and get your code running. I should also say, we got Marta here, Marta's team, and I've worked with Jesus Labarto, watching him do that kind of thing as well. But the number of tool experts we have doesn't scale up with the number of applications we have, and we don't really.
But I think that's also because there's this semantic gap between what the tool produces and what the user actually needs. And I've watched Jesus too, and my God, he's the only one who knows how to do some of those things, right? You're getting these performance profile numbers, and that's what this means in this piece of code, and that is a huge semantic gap. So we either need more people like that, or we've got to bring the tool closer to what the problem actually is, which of course is what we really want to do.
If I can jump in,
Yeah,
I
please.
think it's very interesting, and I think it's just another example of what Heidi said before, which I agree a lot, that one doesn't fit all. So maybe the thing is, do we need the same kind of tools for both kind of users? Maybe for these kind of users, less experts, we need something easier to understand, more aggregated, that will just give some warnings on, look, here's a problem, you need to look in detail, and then the detailed analysis be done, and the tools that do more detailed analysis or are used for that be used by the other kind of users.
Right. So to me, actually, this question is saying we have a problem because tools, most tools are developed for performance engineers. And so we have a problem. How do we solve this problem? Is it that tools have to be built easily, and whoever's gonna try to use the tool doesn't break? Or is it they need better documentation, or I don't know, what's the solution? But it seems to me this question
that's step one, though. If we hadn't got to that step, we can't do the next one. So someone has to know how to use this stuff. And then it's a different question, which is now, so what are you've all seen the picture with the swing, right? The swing is envisaged by different people, right? So we need to then finish up building tools that people can use without those performance engineers.
All right.
Yeah, I think a good first target, as others have said, is you want a tool targeted to someone who wants to use it, right? If somebody isn't even thinking about performance and they've never thought to tune their code, then that tool isn't going to be in their radar. And but whether it's a performance engineer or a scientist who knows, I need to get my job done in this amount of time, I need to come up with a solution in this amount of time, what can I use to help me achieve this? That's where we want to focus. And I also think that one of the things that some tools have started to do and where we could do better is instead of documentation, use directed learning. So as you're using the tool, how do you guide that person to, oh, we saw this with your data, why don't you go try this experiment with the tool next? Here's how you use it. here's the, here's how you enable that experiment, and this is what you should go see. So more of that advice as you start to see results, I think would be helpful too.
So I guess I'll just build on that. I mean, so as someone who used to work on step 2 and stopped step 2 because step 1 was so frustrating, I guess I would say, even once we get past step 1, it was something David said was interesting, that you need to be able to reason to close the semantic gap. And I mean, right now, even just reasoning about like the most primitive constructs in your code is hard, because accessing debug information is hard. People don't build with it, the system libraries don't come with it. I mean, it's not even available anywhere. I think managing performance data, or even in semantic data around it that's much richer than what we have today, is going to be necessary before any of these things people are talking about are actually effective. Because if you don't know, for example, for your fancy new programming model, what maps to your fancy new programming model's fundamental constructs, then I don't know how you scale that out. Like you have to clone Jesus and have him come with PowerBear and gesticulate wildly about the code and give you lots of insight. But until then, until we get something to connect the dots, it's going to be hard. And I guess a lot of these things are fixed because they're really old. I mean, like, so if you look at like how to analyze what shared libraries are in your memory space at runtime, it's done through the System 5 debug interface, which is not, like, it's not what anyone would call an interface now. It's like symbols that happen to be in your binary, and you have to find that symbol and iterate over a linked list, which is not exactly separation of interface and implementation, right? Like, that's old, Dwarf is old, and there are modern things called databases that you can use to query a bunch of that information, and I think, exploring new ways to learn about code and to learn about how things are, actually laid out in an executable would be one pretty fruitful way to go, because we're a long way from anything that would allow us to connect all this stuff.
Right. Yeah, definitely, I agree with that. Okay, so let's move to another question. We have a few questions here from Michael, but I would like to give an opportunity to other people that have posted questions. So let's go to this one. Why isn't there an attempt to get vendor buy-in to build a modernized PAPI that would make tools easier to develop and provide more consistent data? Modernized PAPI. I like that. That sounds interesting.
I mean, isn't that sort of the same? That's sort of the same thing we were just talking about, right? Like, in the sense that, like, I don't know which part of PAPI you're talking about, because, like, I don't know how you modernize PAPI native, but the PAPI high-level interface is something interesting, because it attempts to generalize all the performance counters that you see and come up with something that works across machines. But it's notorious for not being all that general across machines and not being that easy to understand in different contexts. So yeah, I think a modernized PAPI would be great. I also think that it's going to have more structure than PAPI has, right? PAPI has this model of like keys and values.
Right.
And that's I think the data model for what people are actually doing in programs is way more complicated than that, and needs to hang off of programming language constructs and application constructs, data constructs, things like that, like Bart and David were saying.
Right. And I'd like to mention, Heidi, you mentioned that performance counters are difficult to understand. I was wondering if you have any thoughts on I don't know, how to make this space of performance counter better.
I want to relate an exercise. We were doing some profiling back when we were still doing the Paradigm tool, and we were looking at a counter from Intel that was giving us something to do with cache stall cycles, or cache misses. And so we were trying to figure out exactly what this counter was counting and when. And we had complete NDA access with an Intel. So I was given the phone number of the person who did the counter module. And they talked to me and told me all about how it worked, and says, but I don't know what this counter means, because all I do is get a bunch of wires coming from places on the chip, and I count the things coming on those wires. So I was then given the name of the person who was building part of the cache module, and they say, I don't know, there's something in the memory part that's going on that I don't fully understand. So then I talked to the other person, and they said you should talk to this other person. And in the end, with voluntary, cooperative, unlimited access within Intel, I could not find a single person who could truly tell me precisely what the counter meant. I eventually got to the testing group at Intel, which we are not the customers for performance counters. For whoever out there thinks that performance counters were invented for software people, some people
Someone made that comment. They're not.
they're not, absolutely not. They're designed for the testing people to verify their chips. And even the testing people,
Or something, we don't know what.
even the testing people don't know necessarily what the counters mean, but they know in general that when the processor is giving the right results, the counters kind of look like this. When the processor is not, the counters look like that. And so, you know, at best, we're making approximations highly correlated with specific program behaviors on the chips. And we're using that and presenting it with great authority to users and saying, this is indicative that you need to fix this.
Wow, that's a very interesting experience. I was wondering if someone else, Marta or Heidi, have anything to say?
Yeah, I think a lot of, I guess just to add to that, when I've worked in companies that have provided proprietary hardware and counters, what Bart says is right. And the counters were designed for diagnostics. That was their purpose. And performance tools developers latched onto them because they could provide some insight into the why for particular performance bottlenecks. And so then we started making assumptions and getting all excited about what the next generation of counters and how this architecture changed, because the counters changed. When I was with performance tool development, one of the first things that we spend a lot of time on is a new architecture or a new processor comes out, and we go and we figure out what the counters mean by throwing bricks into a dark room, trying to see how they behave compared to how another performance counter on another architecture behaves. And I'm not quite sure what the right answer here is, because the vendors don't actually know either, the vendors producing these counters, as Bart said. And yet the performance tool developers really find some benefit in being able to understand and give some more insight. Our most successful use of counters has really been comparisons, right? Comparing a counter from one run to another, or comparing a counter from one, usually not between one architecture and another. And so it's a challenge. It's something that we've decided is important to use, and yet it's really not its intended purpose. And so I don't have a good answer, but it's a hard problem.
Right. Thank you, Heidi.
Heidi, I do have to say, you just gave me the highlight of the week, the phrase, by throwing bricks into a dark room. I'm going to have to use that every chance I get now. I love it.
When you do performance tools, you kind of sometimes have to do that, right?
Best phrase of the week.
I'm not going into your darkened room.
Okay, so let's take this one. This
Screen.
we have one that is highly voted here, 7 votes from Alan. Can you make an argument for dedicating machine resources solely for performance monitoring, observation, introspection, aggregation, analytics purposes?
Yeah, you can.
I want to.
Yes.
Yeah, I have an argument for that, which is that I think that goes into, the same pot as you have for like build cycles and stuff like that, right? Like if you, the code teams that we're working with are doing sort of nightly builds, they run their test suite and they keep performance metrics on their test suite, right? It's all part, and performance regression testing is a thing that people do. So I mean, to some extent that is machine resources dedicated for that purpose. Now, like, there is like a limit, right? They're not going to let you take the whole machine for a week just to do all the performance scenarios, because if you did that, it would be sort of a waste, right? Because you're using 1 million cycles to save 10. So, you have to have to balance it. But I think you can get a lot of diagnosis done at smaller scales before you start seeing that stuff appear at large scale. And then the large scale stuff is really tricky. You need production measurement for that, and that's hard.
Right, but for this question, I like to bring the topic of correctness. And the question would be like, okay, you're doing this in one machine, but you're going to be running another machine. How do you compare the numerical results, right? Because you're going to be doing performance analysis in one system, and then you have to move that to a different, maybe a different platform, right? So, and may I remember David mentioned this idea of differential debugging.
Yeah, so
and stuff,
that for correctness, it's not so hard, right? Because we're comparing data state. Performance is a harder one because, of course, the performance measures. But in a sense, it's because we're not really defining the performance of what. So
Right.
if you talked about, a uniform performance metric, then of course you could compare them.
Well, there are levels at which you can compare that stuff, right?
Right.
Like, I mean, you may. So, like, one example is with Hatchet, when we, you can compare a call path profile from one machine to a call path profile in another, and you can get a lot out of diffing them, right? If you diff the two, or Hatchet puts the profile in a pandas data frame, and you can subtract the profile on one machine from the profile on another, normalized or not. And, you can look at which parts of the code are you spending more time on which machine and get sort of a high-level view of which modules are performing well. And then, at some level, it doesn't make sense anymore to compare the two because, they're getting their performance entirely different ways, right? Like a CPU and a GPU run, I think the characteristics you're going to look at the low level are really different.
And a cache hit rate is not going to mean anything between two machines.
Yeah, exactly. Yeah, things like that. I mean, I think there's other ways to compare those things, but it's not a call tree diff. I think, but the differential performance analysis is really interesting, and I think coming up with the right shape for the the comparison is the tricky part. Figure out what you want to compare between the machines. Call path profile is a good start.
Right. Okay, so we only have 1 more minute, and probably won't be able to answer all the questions here, but the chat will be open, so you guys can actually go and answer some of the questions in Slido, because the slide is going to be open, and they're not going to close it immediately.
Oh, okay.
But we're going to close the panel anyway.
Let me answer in
You
Slido.
just put another question in, right?
Just put more questions, and then this is.
You can,
We'll be here all day.
exactly, you can put more questions through. That's
Part of
fine.
your
Okay,
answer
let's say
might
this one quickly. The last one. How do we deal with with this explosion of tools, different tools for different architectures, programming models, and programming structures? Any final thoughts on that?
Well, that's the comment I made before. Is I think there have been people who've tried to do it, but we're not focusing on it enough. So PTP for Eclipse tried to do that with pluggable tools, so that you get all of the same infrastructure. It looks the same, feels the same.
Part of the way we try to deal with it, this is several years ago, we decided there were too many tools competing, especially in the research world. So we got out of the end user tool business and started building components. We concentrated on things that we were good at, this analysis instrumentation, and then became the supplier of that other groups and the scalability. And we became a support team. And I think as a community, we do a really good job of collaborating and sharing. It's a very tight community, but I don't think we do a good job of leveraging and building off in a unified way. So I think we could reduce the level of competition down somewhat and work together more as a global team. But funding models and corporate versus academic versus government models and things like that make that a challenge. And tenure models, because you have to get your papers published and things like that. But
Well, I actually like having multiple tools. I like the idea of multiple tools because it reminds me to think, it gives me other ideas, something I maybe didn't think of for a performance tool, somebody else did. And just like an end user, there's no one universal programming language, right? C, C++, Fortran, Python. There's no one universal programming model. There's no one universal runtime for different things. And so we're in this world of complexity. The architectures are complex and the tooling to use those architectures are complex. I just wouldn't want to see one profiling tool on the planet, because then I think that would dull our creativity, and we may not be able to identify some new insight for people who need it. So it's a tricky situation. I hope people find the tool that works best for them.
I wouldn't say one tool, Heidi. I agree with you completely. I would say fewer tools. And we have this constant tension between trying to have the creative diversity and variety out there with the fact that we don't have enough resources, and tools often get the S end of the stick.
Well, that's right. Tool building is not the sexy end of funding.
All right.
It's not
I know,
Unless it's got
I know.
machine learning in it.
That's
right.
right. We all have to move
Wow,
to machine
guess
learning. We all have to move to machine learning, and then they'll dump money on us like it's my style.
I like that one.
I guess
All
I
right.
would say that if you want to reduce the number of tools, like you have to make it easy to run your code with all the different tools and compare them. Otherwise, no one will know how to reduce the number of tools. So like, it honestly, like, if you want to try this, like, I think getting this stuff in CI so that we have a suite of applications that get run with all the tools every once in a while, and you can compare reports or something like that, would be a start.
Yeah. I had a few questions about CI, but I think we ran out of time. I would like to thank everyone. Thank you to all the panel members, and thank you everyone joining us remotely or here. And with that, this is the end of the panel, and I hope you have a nice rest of the week. Thank you very much.
For those of you virtual, hope we see you in person sometime soon and get rid of this.
Yeah, me too. See you.
Bye, everyone.
Thank you very much.
Thank you.
Bye-bye.
Okay.